perfect. So I don't know if you already watched the lecture videos on YouTube channel. Um, when you look at the chapter 8, there's a lot of things going on. It's a very long chapter. So I mentioned it last week too, but when you study for chapter 8, the best one you can study for is the very last page. There's quite a good summary of the reactions. So whenever I do some reaction mechanism over here, only thing you really need to focus on is what makes what product. That's all you need to know. Sounds good, right? So I'm only doing this for you or a better understanding why it happens, but you only need to know what happens. So what product would come up from which reactions. That's all you need to know. Sounds good, right? So they'll make your chapter 8 much easier. So I promise you on the exam, second exam, will be like, it won't be so hard at all. Okay? Just, alright, so the last time we actually left from the epoxidation. So I'll just remind you, this is kind of related to what we're gonna do next with the, we call hydroxylation. Okay? So simply this means we're gonna put a lot of OH, it's a hydroxy group here. But sometimes we can use epoxidation to do this here. So epoxidation is pretty simple. You're gonna use peroxy acid here. So it has to form like anything like this one. Okay? So it has kind of a lot of oxygen there. So one thing we can use is this one. Okay. This is the metachloroperoxy benzoic acid. This is quite a common epoxy acid here. So whenever you have the double bonds here, okay, what you can do, you can try to get heck here, 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 okay. So this is epoxidation because we're going to add the epoxide on this double bond here. So eventually, we're going to have this one. So make sure there's some hydrogen over here, but it's just hidden over there, okay? So whenever it happens, you can do it with the another reaction to make it for doing hydroxylation. So whenever you put it in some acidic condition like this one, what you can do is whenever it has this one will try to grab one of the hydrogen and hydrogen cation over here. So they become, so this one goes here, okay? So it becomes water. But this one becomes this, okay? So we made a bond to the hydrogen here. But they actually don't need the pair of electron here. This is positively charged, okay? So that will give some motivation to move forward with water. So actually water comes in. And so think about this one is kind of on the, like, this is a wedge, right? So it's kind of going this way. So this one can only bond to the bottom one. So in the back side. Now the front side is already occupied this group. So this one you can attack from the back side over here. Okay? So eventually what happens is they're going to have here this one. This is oxygenated the electron over here. This is positively charged. Okay? And then another water will come and grab one hydrogen over here. So, let me show you. you don't have to know this, but if this is so, we can grab one of this one, it goes up here. So then this is gone, this is gone. Then it becomes right? And it only happens, so when it attacks this one here, it goes to this one. So once it's positive, now you got a pair of electron here, so that becomes now a neutral in the OH group. So basically, or you can say either way. So because of this, the epoxidation, before we adding this the hydroxy group here, there was preoccupied at one side. It only attack, water can only attack the back side. So this is why they kind of show you in the trans position, right? One goes up, the other goes down, and kind of thing. So we call this the trans diol. Trans diol. So all means is alcohol, because whenever you have a hydroxy group, you consider them as a kind of alcohol. But di means there are two hydroxy groups. So we kind of call those things like trans diol. Kind of makes sense, right? So only thing you need to know is that whenever you use the epoxidation, it's the epoxide here. In an acidic condition, you get a hydrolyzation here, which is two hydroxy group will be added on this where we can find the epoxide group. Well, initially we already had a double one here. So only thing you have to know, this one, these alkene groups with the peroxy groups in acidic condition, they'll give you a trans diol. That's all you need to know. Okay? So maybe maybe we change this one to this one, right? Then finally, your answer will be obviously trans diol. So just need to do. That's it, right? So this is all you need to know. I'm gonna do this mechanism, but just please remember those for only your understanding. But the key point is what makes what products. That's all you need to know. Sounds good, right? So let me move on. So that will give us the trans diol with the hydrolyzation. So we can have another way to do the similar job, but bit of slightly different way. We call this the ozumium tetraoxide here. So this is what it looks like. So if you look at this, it's somewhere over there. Okay. So we're gonna use this one for also hydroxylation here too. Okay. So I can give you one example. So if you have this one, when it comes in, whenever do L reaction over here, what they can form is this one. Okay. So this is the so this is kind of like somewhere in the plane position. So it comes in kind of they're getting into the those two are on the same face, so kind of on the same side over here. You see, those two bonds are on the same side here, and then you're gonna use sodium bisulfite, okay, and some water here. So what happens to this one here? This one will actually going to cleave those two bonds, and then this water will make this add to the hydrogen over here. Okay, so this one you don't have to know for exact that mechanism over here. So what happens to this one is this will make this one. So this one will actually going to be in the same phase, right? So this is the cis. So ozomium tetraoxide will do the similar job, but because they're coming into the alkene, the double bond position in the same side, that makes cis, because they're going to have a hydroxy group added on the same phase. So it's very similar to what we did with the oxidation and hydrolation, but it's just different position there. So one is a trans, this one is what? The cis positions. So this might be, so I'll give you maybe one more example. If you're using osmium tetraoxide, it's the same, I'll give you the same example over here. Give you, okay. What would be what? So it's pretty much the same thing, but either way is fine. So just make sure they are on the same side and the cis. Okay. Does it make sense? You good? Okay. So this is just the side talk. This one is really toxic. So we can do this too, but normally what they use is the what we call NMO compounds. This will make some cyclic pathway to this one. So eventually, this will becomes or this one, either way, in this type of reaction here. So this, this one will make this one back into original form and can do it in a much more cyclic way. In that way, you don't have to waste a lot of this one. Sometimes we do this because this is really toxic, and also it's kind of hard to control. So they actually wants to use very small amount of it for safe issue. So if you use the MMO compounds, you're actually going to have just small amount of this one keep just circulating, keep being used for making products anyway. But you don't have to know. Okay? So, but make sure you guys remember it's a bit of a difference between these two similar methods, but just you have a hydroxy group on two different positions and in different way. Okay? Can I move on? Does it make sense? You good? Okay. So once again, I emphasize this one again. Only thing you really need to know is what makes what product, sort of things. That's all we need. So the next one is we're gonna break some carbon-carbon double double bond here. So this is we call ozonolysis. We're gonna break the carbon-carbon double bond with the ozone here, O3. Okay, so you can make those two. This electrical discharge, and this is what it looks like. Okay. So whenever you have the double bond here, okay, if you have a double bond here, I'll just put it right on the liquid right here. Okay. So what happens? This one is you have a. So once again, you don't have to know the mechanism. Okay. Just try to look at the final product over here. Okay. So if you do this one, they're going to have this one. Okay. So if you do this one, here just try to look at this one, just for your listening. This one. Okay. So this is, once this form, this is what we call small ozonide. But whenever do this, the movement of the electron pairs, and then becomes the, I'll show you. Okay. Can you see this? Whenever do this, this is broken here. That makes double bond here. That makes negative charge. They donated to make a double bond, so it will be positive. So they separate now, right? And then what they can do is they can move to text like this. So now they really form something that we can use. This is what we call finally ozonide. Okay. So if that is the finally, we have ozonide here. We're going to use some zinc metal, and we sometimes use the acetic acid here and water. Okay, so they can actually break apart here. And these two carbon, they becomes here, here. So when it's broken apart in here and here, they move in an action. The oxygen taken away from the acidic and water. So they become actually two separate carbonyl groups here, carbon and oxygen, carbon here. So this is the final product here. So whatever the R group you had over here, it will be just separated. So now you cleave where you can find the double bond with the two compounds with the carbonyl groups there. So let me give you one example. It kind of makes sense. Okay. Let me give you an example. They will make more sense now. So whenever you have, what can I say? This one right here, right? So basically, what you really need to do here, okay, with the lot of everything, if they all goes there, only thing you really need to look at is here's double bond here, right? You just break it. Just break it right here. So it makes, right? Like this. Just break it here. And you have two carbon right here, right? Two carbon right here. And just add a oxygen with double bond right there. That's it. That's all you need to know, really. What I just told you is just for the mechanism. But on the test, when I give you this ozonolysis, what you're gonna do with the compound with the double bond, just find where the double bond is, break it, and where it's just the two carbons break apart with the oxygen, but it's double bond here, so it's carbonyl groups. So now you have a final product. Sounds good, right? Okay. Can I move on? Is it really? Okay. All right. So let me do this. Let me show you the similar one, very similar one. This is also we try to cleave the double bond, but we're gonna use it with the potassium of manganese here. Okay. It's most importantly, you have to do it in acidic conditions here. So if this is the case, it's pretty much the same. like this one. You have a double bond in the middle here. They will do the similar job. They will do the similar job here. So that's the outcome. Okay, this is the outcome. So let's try to break the double bonds, and where you can find these two carbons where that are broken bonds, just add oxygen with the double bonds there. That's pretty much it. So make sure you guys do this in the acidic condition where you can find enough numbers of the hydronium or hydrogen cation, so you can have this one. This is important because if you have actually like basic solutions or the sodium hydroxide solution, something, they will actually make a hydrolylation over here. So instead of breaking the double bond, you're going to have this one. So it may be tricky sometimes in the exam. Try to remember this one. And also one more thing. Let me change this R groups. This is all methyl group here once. Let me change this one to the lots of hydrogen. This is just one R group, but other one is all like hydrogen, so filled with this double bond here. So in this case, what you're going to get is this one. So you're going to have the acetic acid here and carbon dioxide. If there's all filled with enough numbers of R groups, it also do the same thing what we saw in the organolysis. But if there's filled with a lot of hydrogens, they actually do even more oxidation there. That makes even more oxidative process. That makes even more like different products. That is more with the carboxylic group here, and also the one with the carbon dioxide. So this is just another thing I kind of want you to remember. Okay. This is pretty much the same, just click right here. But this one becomes the carbon dioxide. This one becomes carboxylic acid group. This pretty much. Okay. Kind of makes sense. This is the only additional thing you need to kind of remember from the regular cleavage from the double bonds in the alkene groups. All right, so let me move on. The next one is we're gonna cleavage of 1, 2 diol groups. So I can give you one example here. So as you can see, this is the diol compounds. Here we have a 2 hydroxy group here. You can treat it with the iodic acid here. Okay. So you can treat it with the iodic acid here. This is what it looks like. Okay. And then when it comes in here, what happens to this one is yes. And then what if happens to this one is it makes the, let's see, here. Okay, so this is something you can see over here. This is kind of a, so as you can see, you have a, can you see this one? I'm not gonna tell you in detail. There's 4 oxygen here, but there's the 5. So there's a hidden mechanism I didn't tell you. The actual outcome is the water over here. Okay. So what happens to this one is you have a series of the movement of the reaction over here. You see this is also broken apart too. Right? You see once they make some like a cyclic intermediate structure, they're going to break apart when you move the electrons in this way. Okay? So the outcome is pretty much the same. So this is break apart. So this is a break apart, but those groups become carbonyl group, not the hydroxyl anymore. So you can do it with the iodic acid here, because this type of intermediate will induce this type of sequential movement of the electron pair. Then that makes breakage on this part that becomes the carbonyl groups. As you can see, they become double, gone, and break apart. So here, this. So here's the thing. You may wonder if I'm going to give you like, this is a diol, right? So maybe I can make two steps. You have a alkene groups here. You can actually hydrolyze with the, some type of the reaction like we just talked. And then you can treat it with the polyiodic acid here. You can also mix them two carbonyl compounds over here, sort of things, which I'm not going to do. You only need to do this one-step mechanism, that's all you do. Does it make sense? So I'm not going to trick you with the alkene groups becomes diol, and then just to cleave the carbonyl groups down. You just need to know this one, here comes and break apart. I'm only going to ask one step. Not going to make a series of steps and steps. It might be a lot of things to consider. Sounds good. Do you have any questions? You good? All right, so we have to move on. So once again, only thing you really need to know is the products. It's always good to understand why it's happening, but it's really, we really need to know is the product, what kind of product we can make, so we can actually use it for any chemical knowledge or experiment. So this might be probably the last one. So we call this the addition of carbene to alkene. So basically, if you have some kind of a form that it looks like R2 carbon with the one lone pair here, it's two electron or pair of electrons here. This is what we call carbene. Okay, so you can try to use this one for the alkene groups too, like this one. Here's one way, but one of the really good one is you can have this compound over here, okay, and you're gonna treat it with the strong base, okay. So what happens to this one is you have hydrogen over here, right? You have a hydrogen over here. This is simply the same as these two, right? Because it's the strong base. We should have a lot of numbers of hydrogen anion. So we'll grab this one. Well, actually, this oxygen will grab this one. So this one goes on here. So the pair of electron on this bond here will on to carbon. So then you're going to have a pair of electrons on here. Okay. So this will make carbon negative because you have 1, 2, 3, 4, 5. Okay. So that makes the enough motive for this one to leave, one of this to leave, like this, to be more stable because it's negative charge. So they want to become, there's one, right? And then they're going to have this one, okay? But now the carbon is 1, 2, 3, 4, neutral now, right? No more negative charge. But with the lone pair, this one will have some weird, like kind of I think it's kind of weird structure over here. So if that is possible, this is, do you guys remember the electron domain structure? Electron domain structure, you have a molecular geometrical structure. You also had an electron domain structure. So molecular structure is what? It's bent, right? But the electron density structure is tetra. It's actually triplanar. Because we, in that way, we consider lone pair as also part of your structure. You guys remember this, Jenkins 2? So this is kind of weird one even. Let me tell you why. This is not tetrahedral anymore, but this is now trigonal planar. So they're on the same plane. So that means even though they had over here, there's a p orbital here because the lone pair is empty now. Because there's no two bond. Instead of two bond, there's only one lone pair. That makes one p orbital empty, vacant. So that is kind of explain why red with the alkene. If you think about it, all the other potassium permanganate or aluminium tetraoxide, all with oxygen or carbon, they always had some the different change in electric potential and everything to make some difference and make it more stable products over here. But this one is simply from carbons. So they don't have much of the reaction motives here because they're all carbon. They're not really different elements here. But they still do this because they're not attacking carbon here. Well, actually attacking carbon here. But if this one happens, this one, the one in the pi bonds, will attack the empty p orbital. This is why they can still make some interaction here, even though between the carbons, the lone pair. That kind of gives the reasoning, rationality to make this reaction forward. So if that is the going on here, what happens is this one. So as you can see, this is in the cis position here, right? So you don't see it, but it's hydrogen over here. Okay? So they keep the same position, which is the cis. You see hydrogen, but they all cis position too, and that makes carbon and chlorine this way. But they're on here, so that makes the tetrahedral, semi-tetrahedral structure, but have more like it's kind of hard to explain. That goes on here, and here, and here. So that makes more stable position where you can see. Okay, so this is one good example for like a carbon addition. Instead of this orbital, we actually put a chloro, so it's kind of dichlorocarbon addition, but it's pretty much just the same job. Kind of makes sense? Kind of? Kind of.
That
Okay.
one was a little more difficult than the.
Oh, really? This was a bit more difficult. So the only thing that makes kind of special, make this special, is this bacon p orbital over here, because it's really kind of not quite makes sense to make this the empty p orbital kind of involved in this type of attack here, because normally this carbon, there gotta be kind of a great amount of the like a free energy change motivation, like or something, that then they can have enough energy to make a bonds. But for this case, is kind of special because of the lone pair. So that makes the bacon p orbital, that makes this one more available, accessible to the tent. So that makes this carbon, so it makes kind of a ring structure. But once again, the only thing you really need to know is the product here. So let's say we have this one over here, right? We treat with the this same condition over here. What you really need to do is this one. So basically, you kind of adding this one. Obviously, this has to be. This is kind of a in this part it's in a cyclic propane kind of structure over here. Right? They gotta be all in the same plane. But the ones over there in the hydrogen here should be on the same side because they only coming into these two positions here. They coming into the same plane, so it goes on to this side. So those two can keep the same position where it was. If it's a cis, it'll be cis position. If it's trans, it will be trans position. The point is you don't change the cis or trans form you see from the double bond initially, and you can keep it from this cyclic form because you also cannot rotate the ring structure like a double bond. So you can actually need to tell if it's cis or trans because this is not the single bond anymore. Usually they kind of either break it or make it single bond, or then you don't have to worry about much in the stoichiometry for certain case. But this one is because the way. Okay, let me give you one more example. It's very similar to this one. Okay, so this is what we call, this is still same, but this is certain similar kind of special name for it. It's a Simmons-Smith. It's a Simmons-Smith reaction. So instead of the dichlorocarbon, we're actually going to use the, well, I can show you here. It's kind of weird for me. What you need to do, you need to do diiodomethane here, and then you also do that with the zinc. Kind of, it's really zinc, but with a bit of a copper alloy structure. So if you have a certain type of, I'll give you the same. This one over here. What happens to this one is they kind of makes this weird structure. Here. So these two interact each other. It makes this form over here. Okay? And then whenever you have a double bond here, this carbon. Oops. So consider those all still in the same position, like a cis position here. They actually attack the carbon here, and they goes up. Obviously, this is wants to take electrons for sure, right? And then this bond will attack here. So they just break apart. This is pretty much the same, but they only comes with not 2 chlorine anymore. It's 2 this hydrogen here, right? So it becomes. This one. So you see these are on the same cis position here. So when they make a kind of ring structure on the top, they also gives the same position on this, the 2 R groups here, and you don't see it, but there's a hydrogen too. There's kind of a where you can find it, but there's a hydrogen too. But you normally don't do this. You don't normally show the hydrogen on the skeleton structure. This will be the answer. Okay? Maybe. So if I give you this one, it could have been what? This one. Because then in the different position. Because you don't change it. So that's really something you really need to worry about. You don't have to do this one for me, it's okay. But this actually forms the ring structure, so that will make your position need to be somewhat clear with the cis or trans position. And then you can actually use it from the original form, which was trans. They just keep it the same on your products here. So if I give you maybe this one as your one of the choice too. So you remember this one, right? I don't normally show you the hydrogen. We don't normally put the hydrogen on here. So maybe you can say this is the one. This is the other choice. And you still need to choose the best one. That's it. And if that was the cis, choose this one. So it doesn't matter. If you do this one, this is also cis too. They're on the same side too. So either way is fine. Right? They're all trans too. You just need to look at it. Okay. Kind of makes sense, right? I think this is a congruent this one. So yeah. So 40 minutes. Okay, so I'll just stop here today. I'll try to finish up the chapter 8. Hopefully this Wednesday, and we can move on to chapter 9. But just letting you know, chapter 8 is really long. A lot of things to memorize, kind of stuff. So once again, just try to look at the what reaction makes what product. That's what really you need to study for, and that will make it much easier to study. Okay, sounds good, right? Good. Okay, thank you. That's it for today.